Yes, seems about time. I first saw this guy a couple of years ago when we were still back at the cinema, and he amazed me then. I had the pleasure of being at his session, one of his sessions at least, last year. He amazed me then, so I'm really looking forward to be amazed this year also. Please give a large hand to Mr. Simon Ritter.
Great. Right. Is the microphone working? Is the microphone working? Is it? Yep. Okay. Good. That's better. Right. So, good afternoon and welcome to the catchily titled "Is it a car? Is it a computer? No, it's the Raspberry Pi Java Carputer." I noticed that they had to shorten that a little bit on the sign outside. What I'm going to do this afternoon is talk about Raspberry Pis and computers and cars. So I have to admit that I am what we describe in English as a petrol head. I like cars. I'm also, as my wife describes me, a geek. So I like electronic things. So it seemed like a logical thing to join the two together and have some fun in terms of figuring out what you could do with cars and computers. Now, as an Oracle employee, the first slide I have to put up for you is the normal legal slide, which says that this is not necessarily intended to outline our general product direction. I think I'm fairly safe on that one, in that I don't think we're actually going to be developing this as a commercial product. Having said that, though, there are a lot of things going on in the whole field of cars and the development of computer systems for cars. So you may well see things like Java, embedded Java, in cars in the future. Now, in terms of the agenda, I thought we'd talk a little bit about cars and computers in general, to give you some ideas about how things have changed over time and what kind of things happen in modern cars, because it's very interesting when you start digging into the details. We'll talk a little bit about the Raspberry Pi, the background to that, and how that came about, why it's a very good platform for developing these types of applications. I'll talk a little bit about embedded Java and JavaFX, which is what I used to develop the software for this. And then I'm going to spend most of the time talking about the Carputer that I built. And so this is the box that I've got at the front of the stage here. And then I'll give you some demonstrations at the end. Now, clearly, I don't have a car here with me, so the demonstrations won't actually involve any driving, but I do have some videos, and I can actually show you the system running with some simulated data. Let's start then with cars and computers, and looking at some history. So let's have a show of hands. Who here has a car? Good, okay. And who has a computer? Right, good audience. Okay. Now, I went back and I looked at what my first car was. And this is it. This is actually my first car. A Mini Clubman. Anybody else have a Mini at one point? Yeah, a few people. Great car. I really liked it when it worked, because it was such a simple car in terms of technology. So the engine, as it says here, it had no electronics at all. It had some electricity involved, but there were no electronics unless you counted the radio, which got stolen at one point. So then there was no electronics in my car. So everything was purely electromechanical. Anybody here remember points? Goodness me. Oh dear, only a few people. Feeler gauge and setting the points. Okay, right. So old cars like this had a distributor, which meant that the ignition for the cylinders was a mechanical system, and it just span round, open and closed a switch, and that would pass the electricity to the spark plugs. It had a carburetor. Anybody remember carburetors? Okay, that's better. I don't feel quite so old now. It had drum brakes, so no disc brakes, no ABS or anything like that. It didn't even have an alternator. It had a dynamo. And then in terms of the luxury features, it had lights, it had a horn, it had windscreen wipers, which worked sometimes, it had a fan inside, which worked very rarely, and it had an ignition switch. And that was basically it in terms of the electrical systems in the car. And then what I did was I dug out the Haynes manual. Anybody here remember Haynes manuals? Oh, good, okay. I dug out the Haynes manual, which I still have for my first car, and I downloaded or copied this. This is the wiring diagram for the Mini. So despite having only a very few number of electrical components, it's still quite a complicated wiring diagram because we've got all these different bits and pieces that need to be wired together. So that's the wiring diagram from a 1970s car. Let's skip forward a few years, and here is my current car. So I'm currently driving an Audi S3. This has lots of electronics in it. So we don't have to worry about things like points, we don't have to worry about things like the distributor, because now we have an engine control unit. So it's all electronic, it controls how much fuel gets sent to the engine through the fuel injection system, there's electronic timing, all of that's handled by the engine management unit. That's very interesting because, of course, it has in there a mapping, and that's designed to control how much fuel and when the timing of the ignition is set based on how you're driving. And what you can actually do is you can change that mapping. And so, not this particular car, but the previous cars I've had, the last two cars, I've actually had it remapped, and that can actually give you more horsepower. And it's really kind of weird to think that you can actually improve the performance of the engine simply by changing the mapping in the engine management system. But you can do that. It has a fly-by-wire throttle. So unlike in older cars, the throttle is not actually connected to the engine physically. It's actually just a potentiometer that registers the position when you press down on the pedal, and then that sends a signal to the engine management unit, which then controls the amount of petrol. It has anti-lock brakes, it has an electronic stability program. It's quite funny actually, because a friend of mine had a BMW and he pointed out in the instruction book that it says the BMW has a very sophisticated electronic stability program. Please bear in mind that this cannot defy the laws of physics, which is quite true, because you can't actually defy the laws of physics there. My car even has a thing called magnetorheological suspension, which basically means that the shock absorbers are filled with a liquid which contains like iron filings in it. And then you put a big magnet around it, and by changing the magnetic field, you can change the viscosity of the shock absorbers, and then you can change the way the suspension works. It has satellite navigation, it has auto-sensing wipers, it has all sorts of lights and things like that. So what does the wiring diagram look like for this? Well, it's actually a lot simpler, because it would be just too complicated to wire it up the way that we used to do things. So rather than having individual components wired directly to each other and everything having to be wired to everything else, the manufacturers of cars have now switched to the idea of a bus architecture. You know, we're familiar with that in terms of computing. We understand how that works. So you have a bus which goes around the car, and then you attach different parts of the car's electrical system to that bus, and you send messages back and forth. So each part has an ID. You can send messages from one device to another using the ID and using particular codes to control things. And if you look at the way that cars are designed, you'll find that there's more than one bus, so that you can isolate messages depending on, well, how important they are, I suppose. So in the Audi, you've got a powertrain bus that controls the engine systems and things like that. You've got the convenience bus, which is things like the wipers, the lights, and so on. And then you've got the infotainment bus, which controls the radio, the satellite navigation, the phone system, and all those sorts of things. So you can see that the idea of having that bus architecture now means that you can send messages around. And what that leads to is some interesting potential. So if we look at the protocols that are used in the car systems, what you'll find is that pretty much every car that's been manufactured since about 2000 now has a connector under the dashboard. If you go to your car and you look underneath the dashboard, you'll find a connector that looks a bit like a SCART connector, if you remember those, and you can plug things into that. Typically, the garage will plug in a device to that, and they'll be able to see whether there's any error messages that your car has recorded whilst you've been driving it. So if there's something that needs to be fixed, some of those things can be detected, and then they can go and change what needs to be done. They can also reset the service indicator to say it doesn't need to be serviced anymore. And like I say, you can actually download a new mapping for the engine management system through that service port. Or at least you could in the past. One of the things that rather annoyed me was when I got my new car, I discovered that Audi had since decided that even though I had bought the car from them and then I owned it, that I couldn't now change the mapping because they put like a checksum on it, which I think is very unfair. But now you have to actually solder things into your car to change it. In terms of the protocols that are used for this, we have a variety of different standards that are available. So there is this thing called EOBD2, the On Board Diagnostic System, and that has a particular type of connector, as I say, and then there's different sort of protocols that are used at the wire level in terms of sending messages around the car. So there's different ones in terms of you can do pulse width modulation, you can do various variable pulse modulation, all sorts of things like that. And the most common and probably the most significant one from what we're going to talk about is the controller area network, or the CAN bus. And this is what's used by a lot of the manufacturers to determine the ID of the devices that they connect to the bus and then the control signals that they send in terms of the messages. And then in terms of how that works, you have either an 11-bit ID or a 29-bit ID, depending on how sophisticated your car is. And then the speed of transmission is either 250 or 500 kilobaud. So you can send quite a lot of data over this network, which when you're dealing with things like braking systems and critical systems, you do need to be able to get your messages to the thing that needs to understand about, okay, you need to change the way the brakes are working and things like that, because it can be very important. So that's the sort of basics of car systems. So let's just talk a little bit about the Raspberry Pi. Because, so who's got a Raspberry Pi here? Oh, most people, good, okay. Raspberry Pi is a thing that is close to my heart because it dates back, in terms of where it comes from, quite a long way. The Raspberry Pi project was started back in 2006, and what was really the motivation behind this was that a number of academics in the UK were getting very concerned about the way that we teach computer science to students at school. So before you go to university, we have this thing called ICT, Information and Communication Technology. Now, my son is 7 years old, he goes to school, and one of the things he has to do is ICT. ICT to him is to learn how to use a word processor. And unfortunately, that's not computer science to me. And what you find is that even as you go into like secondary school, they're still teaching things like how to use a word processor, how to use a spreadsheet, and if you're really lucky, you get to program in HTML. Now, I'm not sure HTML is actually well, it's not a programming language, so that's not really a good way of teaching children about how computers work. So the academics decided that ICT needed to be overhauled. And one of the things that we needed was some way of getting children and students interested in how computers worked. The best way to do that was to give them a computer that they could play with and they could do interesting things with. And the kind of design ideas behind this date back to the BBC Micro and a program that the BBC in the UK did called Micro Live. So anybody remember the BBC Micro? Who had a BBC Micro? Good, okay, there's at least 2 people in the audience who had a BBC Micro. This was my second computer, the BBC Micro. The first one was a TRS-80. Anybody remember TRS-80? A few, oh, more people actually. Okay, so they decided that they wanted to build the Raspberry Pi as a sort of modern day equivalent of the BBC Micro. And so they launched it nearly 2 years ago, in fact, yes, coming up to 2 years ago, on February the 29th, 2012. They had an initial production run of 10,000 boards, and they thought, yeah, we'll probably do well, we can probably sell all of those boards without too much problem. And what actually happened on that day is so many people tried to buy these boards that there are 2 websites in the UK that really are distributors for electronic components that are used by all the big manufacturers. One is called RS, Radio Spares, and the other is Farnell, or Element 14. And basically, there was a denial of service attack on both those websites by people trying to buy Raspberry Pi boards. And it resulted in both their websites being unavailable that day because they just couldn't cope with the demand. Well over 1 million boards have been shipped so far. Clearly, some of them are owned by people in this room, and they are proving to be very popular. I'd say they're probably proving to be more popular with people who are not at school than they are with school children, but it's certainly still driving the idea of education. Now, from the point of view of the specification for the Raspberry Pi, for those of you who don't actually have one, its CPU is an ARM11 V6. It's running at 700 megahertz, so that's not very fast by modern standards. It's in a single on-chip package that came from Broadcom. You can now actually overclock it to 1 gigahertz without invalidating the warranty, which is quite nice. I certainly run mine at around 900 megahertz, and I've never had any issues with stability. I've never had any issues with it crashing or anything like that. Memory is now 512 megabytes. The first boards only had 256, but now they all have 512. From an I/O perspective, the idea is to make it cheap. So it's only sort of, 30 euros or thereabouts. And you provide a lot of the peripherals that you would expect if you were buying a PC. So you find yourself a USB keyboard, you find yourself a USB mouse, you find yourself a TV, which has HDMI as an input, so you can connect it using HDMI. There is an audio out connector. There's no audio in, but there is audio out through a standard 3.5mm plug. It has 2 USB ports. It has Ethernet, so you can connect it to a network. If you want to do Wi-Fi, you can use a wireless dongle. You can plug that in through USB. And then the really interesting bit is where you get into the header pins. So the header pins allow you to connect other types of devices. And there's general purpose I/O, there's a UART for serial communication, there's SPI and I2C, which are well-used standards for connecting sensors and actuators and things like that. Now, from the point of view of using the Raspberry Pi in the car, there are a number of advantages for why this would be a sensible thing to use. First is it's actually got plenty of computing power. Now, yes, it's 512 megabytes of memory, it's 700 megahertz processor, which might not seem like much, but that's about equivalent to a Pentium-class computer of the late 1990s. And we certainly used to do a lot with machines in those days. So we got enough computing power there to do most of the things you would expect to be able to attempt with this kind of device. The other important thing is how you power it, because if you try and put a big PC in your car, you need a 12-volt power supply, you need a 5-volt power supply, you need lots of current, you need lots of cooling because it generates lots of heat. The nice thing about the ARM processor is it's low power. So you can power it off a single USB 5-volt supply. You can, with less than 1 amp, because it doesn't take much power, it runs cool, so you don't have to have a big cooling fan involved. So it's nice in that sense for actually being able to power it off the car. The other thing is, in terms of storage, there's no hard disk drive in the way that you have in a laptop or a PC. And that means that you don't have the problems of vibration that you would have in trying to put a laptop or a PC in a car. Storage is through an SD card, so you stick the SD card in, you boot off that, and you can write data to it, you can read your applications from it, you can use Linux from it. That all works very well. Again, in the car environment where you've got vibration, those types of things, it doesn't cause the SD card to have any problems. Another nice thing about the Raspberry Pi is it's supported by Java. So we've done a lot of work with the Raspberry Pi Foundation to make sure that Java runs really well on the Raspberry Pi. And in fact, just at the end of last year, we got to the situation where we did a special licensing deal with the Raspberry Pi Foundation, and so now the Raspbian distribution, which is the standard one from the website, comes with Java SE7 embedded, already installed on it. And so that's good to be able to use that. We've also done work in terms of JavaFX to make sure that it's tuned. The graphics that JavaFX uses work very nicely with the GPU in the Raspberry Pi. And that's, again, one of the nice things with the Raspberry Pi. Its processor might not be that powerful, but it's got a really nice GPU built into it that can do sort of multimedia and stuff like that. Looking at just a little bit about embedded Java and JavaFX, just to kind of go into a bit more detail about that. One of the things that we're doing is really trying to move Java so that we have a single platform. In the past, we've had Java ME for micro devices, embedded devices. We've had Java SE, the standard platform, and we've had Java EE for the enterprise. And in terms of Java ME and Java SE, what we really want to do is to sort of migrate them so that we have a single platform that will apply to all of the types of devices that people want to program in. Currently, we're not quite at that point yet. Java ME8 will make some changes as we move to Java 9. There'll be more things, especially around modularization, that will help out on this. But Java will fit in very small devices, right down to, if you look at Java Card, in literally the tens of kilobytes of memory. And then Java ME will pick up at less than 1 megabyte of memory and then move on from there. So that it will cover a wide range of different types of devices. Java ME embedded 3.3, and now, as you'll see next month, there'll be Java ME 8. What we're doing there is we're actually improving things. So you've got things like the connected limited device configuration, which is the basic specification for the JVM and the minimal set of class libraries. One of the nice things we've introduced there is a device access API. And this is a new thing, which gives you access to all of the Raspberry Pi specific things like GPIO, UART, SPI, I2C through a standard interface. We're actually looking at migrating that into Java SE embedded as well, because that will make life a lot easier. So there's various things that we're doing around that which will improve the way Java ME works and make it more suitable and migrate to Java SE. Java SE embedded, we currently have early access of Java SE 8 embedded, and again, we've tuned this for the Raspberry Pi, as I said, so making sure that it works with the fact that the Raspberry Pi has hardware floating point acceleration. It's not a standard part of the V6 ARM architecture, but it does have it, so we wanted to take advantage of that. Various compiler optimizations we've done to improve performance on there, making sure that JavaFX runs nicely on there, things like that. So there's different things that we're doing really to try and improve the way Java works in specifically the Raspberry Pi kind of environment. A little bit about JavaFX on embedded devices. JavaFX has been around for a while now, and what we're trying to do is target JavaFX at embedded devices to give people a way of creating rich, interesting user interfaces for embedded kinds of devices. Now, we don't currently support the full feature set in terms of the things that are available in JavaFX. There's a couple of notable exceptions. One is that we don't support the web view component, which means you can't render a web page as part of your embedded application. Really, the reason for that is because if you look at the WebKit rendering engine which we use underneath, that is actually over half the size of the JavaFX libraries. So it's a big piece of functionality in terms of the footprint. So we decided we're not including that at the moment. We may do in later releases, but not right in the moment. Similarly, we don't have media playback support included. Again, that's something we are looking at sorting out, making sure that will work. For the application I was working on, it's the sort of thing which I didn't really think I needed to have video playback, so I could do without that. Another thing with JavaFX is to remember that in an environment like this, you are constrained in terms of your resources, so the amount of memory you have, the amount of processing power. And so thinking about the way the display works is quite important from avoiding having very, very complex scene graphs. So lots and lots of nodes. Might look very pretty, but it might not run very well in terms of performance because of the footprint of the machine. So Gerrit and I were sort of talking about this a while back, and he recommended that you have less than 50 nodes in a particular scene graph for this type of environment. I've certainly not found that I've run into any problems. I think I've gone over 50 in some places, but it seems to work pretty well. But it is something to bear in mind if you get into very complicated scene graphs. So let's talk about how we build a Java-powered Carputer. Now, first thing we need to do is figure out what are the design objectives for building a Carputer. And so I thought to myself, well, what I really want to be able to do is display extra information. Obviously, in my car, I can see how fast I'm going, I can see the speed of the engine, I can see how warm the engine is, I can see how much petrol I've got left, things like that. But it'd be nice to get extra information. So finding out, how much power the engine's generating, how much torque I'm getting from the engine, the load that's on the engine, those types of things. And then also to look at driving style. So recording things like the throttle position, recording things like the angle of the steering wheel at any given time, braking force, those types of things. And also looking at the G-forces that are being experienced by the car. So as you're driving around a corner, just how much G are you pulling in a lateral way and things like that. And I thought it would be nice if we could record all that data and display it as you're driving around. But obviously, as you're driving, you're not able to really study the display, or at least you shouldn't be studying the display. And so what we want to do is to record that data and then be able to play it back, and we can see, well, okay, we were doing this particular maneuver at this point and, you know, pulling that many G or doing whatever. And really sort of playing at Formula One. So who here follows Formula One? A few people? Okay, so on the TV, if you watch Formula One, they have a lot of telemetry that they display. So you can see things like, you know, the amount of energy they got left in their KERS system. You can see how many G they're pulling and stuff like that. So it's quite interesting to see what's going on. So the key part of getting this information is interacting with the OBD2 interface, this socket that you've got underneath the dashboard of your car. And so if you go on eBay, you can buy a box like this, literally for sort of $10. There's two different sort of variations on this. One is a Bluetooth version, one is a Wi-Fi version. Wi-Fi version is a little bit more expensive, but the Bluetooth version, like I say, is literally about $10. What it does is it plugs into the service port, it then communicates using the appropriate protocol and allows you to interrogate the system to get the data from it. In terms of the one I've used, it's basically got a fixed IP address and then it creates like a little Wi-Fi hotspot that you can connect to using ad hoc networking. In terms of the Raspberry Pi, it's fairly straightforward. Set that up so it will work with it. You configure a static IP address in the etc. network interfaces file, and you tell it that you want ad hoc networking, so it's doing point-to-point rather than going through a router. Once you've got that, the way that you communicate with the box to get information is in basically two different ways. If you want the OBD2 information, or if you want to communicate with the actual box itself to change the settings, there's a set of AT commands. Okay, so let's see how old people are. Anybody remember? A significant number of people remember AT commands for modem control and things like that. So it's a very simple protocol. You just send AT and then you send some character sequence, and that tells the box what it is you want to do. If you don't use AT commands, the second way of communicating is to essentially send data onto the CAN bus. So you can bypass the OBD2 protocol and you can send data directly to the CAN bus, which means you can interrogate devices and say, give me the information about this. Or you can potentially send information and say, I want to override something. So I want to wind the window down, or I want to behave as if a switch was pressed, things like that, which potentially can get a bit scary. Touchscreen. I love eBay because you can find all sorts of wonderful things on eBay. And so I was thinking, well, I want to have a screen to display the information. And I found on eBay that there was a nice screen that was being sold, and it's actually an in-car screen. So it's a 2-DIN size screen, which comes with a touch screen capability, and it also has HDMI input. So they marketed it specifically for the Raspberry Pi, but it was originally intended to be an in-car system. So that made it very simple from the point of view of connecting it to the Raspberry Pi. From the point of view of the touchscreen capabilities, it was just a USB connector which you could plug into the Raspberry Pi, and then it would behave as if it was an input device. That was one of the things that proved a little bit complicated in terms of getting the touchscreen to work. So when I first plugged it in and I looked at Linux and it said, yep, there's a device there, it recognized it, it had the USB manufacturer ID, it had the device ID, that all seemed good. It created some devices for me in /dev/input, and there were two of them. There was Event 0 and Event 1. When I tried to use JavaFX with it, I couldn't get any input to work. If I used the normal desktop environment on the Raspberry Pi, it would work quite happily with the touchscreen, but when I used JavaFX, it wouldn't register any events. So I talked to the engineers on the JavaFX team who were dealing with this kind of thing, and they sort of looked at the data that I was sending them, some debug information, and they said, yeah, it looks like it's because it's trying to use event 1 or event 1 is generating the real events, and JavaFX uses event 0. So they said, well, we can do a special build for you if you want. And so I was thinking, oh, okay, yeah, I'll probably have to do that. And then one day I was thinking about it, I thought, ooh, actually, no, I can just bypass that completely. And so necessity is the mother of invention. And I thought, well, okay, let's just delete event 0 and then recreate event 0 with the same major and minor device numbers as event 1, and then lo and behold, everything works quite happily. So I have a little script that I start up at boot time because it recreates the devices every time, and so I just have to run this little script which deletes the particular device, recreates it with a nod, and it's all working quite happily now. In terms of the hardware architecture, this is what it looks like. So we've got the Raspberry Pi in the middle there. I've got a USB Wi-Fi dongle, which communicates obviously wirelessly with the Elm 327, which is the box that plugs into the service port. I've then got the touchscreen, which is connected to the HDMI. The USB for the touchscreen plugs into the USB port. And I've also got an accelerometer. So I can measure G-force, I can measure inclination, things like that. And so that's connected on the I2C bus through the header pins that are available on the Raspberry Pi. And then in order to power the Raspberry Pi, I've just got a converter which takes 12 volts from the cigarette lighter and then converts it into a 5-volt micro USB connector so that it'll power the Raspberry Pi. Putting all that all together, what we end up with is something that looks like this on the inside. So this is my box here. So a couple of things to note about this picture. The first is that this is one of my kind of projects, because I firmly believe that any good software project should involve woodwork. So I got a chance to use some wood in order to mount the screen in the box, so that was good. The other thing you'll notice is that I couldn't find a short HDMI cable. So I ended up with a 1 meter HDMI cable that actually needed to be about 8 centimeters long, and so you end up with this kind of coil of HDMI cable wrapped round. I did subsequently find a shorter one, but because I'd already fitted it, it didn't seem to be too difficult to just leave it there. And so I was lucky to be able to use there were a couple of mounting posts on the back of the screen, and I was able to put a couple of bolts in there and then mount the Raspberry Pi on the back of that. From the point of view of the accelerometer, this is a really nice little device that you can get. It's from SparkFun. It's an MPU 9150, which has 9 degrees of freedom. And so it's about $45, maybe $50. So it's not fantastically cheap, but it's really nice because it has an accelerometer that works in 3 axes, so you can tell when it's being moved in a particular direction. It has a gyroscope that works in 3 axes, and it also has a magnetic sensor, so you can use compass, and that also works in 3 axes, so it doesn't matter what the angle the device is at, you can still get a reading for the bearing. So that actually gives you the ability to monitor motion really quite accurately. In terms of the communication, it uses I2C, so it's standard bus architecture and protocol. To get that to work with the Raspberry Pi, you've got to do a couple of things. You have to edit the etc. modules file to make sure that the I2C BCM 2708 and I2C dev devices are available, and then you can figure out which address the device is on by using I2C detect -Y1 to get the address. I got the gyroscope and the accelerometer working quite happily. I didn't get the compass working. I haven't had a chance to go back and look at that yet. It seems to be a little bit more complicated in terms of the way that it works. I think it's on a second I2C bus. There's just some additional sort of magic that needs to be applied to that to make it work. In terms of the code, it's pretty straightforward, because what you end up doing is doing some I2C programming. So you basically get the bus reference for the I2C bus, and then you tell the bus which device on that bus you're talking to, which in this case is 0x68 hex. And then you basically send a sequence of bytes to it, basically say reset, and then start reading. And you can set the configuration in terms of both the gyroscope and the accelerometer, because the accelerometer will read, I think it's 2G as a maximum. It'll read 2G, 4G, or is it 6G and 8G? But it has a different set of readings that you can use. I set it to 2G because I figured that if I was going to get anywhere close to 6G in my car, that was going to be very bad, any direction. So I set it to 2G, and that seems to work quite well. And then you basically just say, okay, I want to read the data from there, and you can just get the information as you want it. So you poll it, basically. One of the things you have to do is you have to compensate for gravity when you're dealing with acceleration, because basically the Earth sucks. So what we do here is we say, well, if you tilt the device, that will, because it measures acceleration relative to gravity, so you've got a constant acceleration downwards, clearly. If you tilt it, then it means that you've got to start compensating for the fact that there's an angle involved. So what I did was I said, okay, let's essentially ignore that problem. So we'll mount the device so it's vertical, so the accelerometer is held vertically. So we know we've got one axis where it's actually going straight down, and then we'll ignore the fact that as you drive, you do roll a bit and you do dive, and there's both pitch and yaw involved in driving, but for the purposes of this demonstration, we'll just ignore that. There are some other things you could do, so we could actually say, okay, let's take the gyroscope information, we'll understand what speed we're moving, and we can detect the roll, and then we can compensate for that, but like I say, that was too much mathematics. Then, having got some information from the accelerometer, get some information from the car, we can apply some relatively simple physics, and we can say, okay, let's calculate the power and the torque that's being generated by the engine, and that will be at the wheels. So if you look at the way you do that, torque is taking the mass of the car times the wheel radius, times the rate at which you're accelerating in G, and then if you want to convert that into somewhat more familiar units, certainly for me, pound-feet of torque, then you calculate it by multiplying by this magic number. Power, in terms of brake horsepower, is just torque in pound-feet times the engine RPM over 5252, and again, that gives you the results you're looking for. Again, we need to be a little bit careful about understanding that the results are not going to be fantastically accurate, because all of the things in red are going to be a little bit, they're going to have an error associated with them. Now, I know that I can detect, or I can get the mass of the car because the manufacturer publishes that, but then I've got to account for the fact that I've got so much petrol in it, I've got me in it, other bits and pieces that get added to the car in terms of car seats and things like that. The wheel radius, yeah, I can measure that, but of course it's not perfectly circular because you've got the flat bit at the bottom where the tyre deforms. Acceleration, because we're not taking into account the pitch and the yaw, so there's various things there. But it's worth looking at the data just to see how close it is to what you would expect it to be. Software architecture. So what I wanted to do now was say, okay, I've figured out what kind of information I want to display. How do I then do this as a sort of an interface? And so I thought, right, okay, I need like a splash screen so I can do something interesting. Then I'll display information in terms of basic data, some more advanced data, G-forces, and then I'll do some graphs so I can see how things are moving over a period of time. One of the obvious things about this is we need a simple user interface. You don't want a complicated thing where you're trying to do this as you're driving, because it may distract you from the driving. Certainly if you look at how difficult it is to interact with a satellite navigation system, you don't want anything that's going to be too complicated. Similarly, trying to read numbers is not going to be very easy, so you want some kind of graphical representation of things. Touchscreen, just use that to switch between screens, so make it nice and simple. One of the things I had in mind was to take the information from the CAN bus and then determine when you're pressing some of the switches on the steering wheel and maybe use those to communicate. So then I thought, okay, UI, let's get some ideas from what other people have done. So this is from the Renault Megane Sport. Anybody have a Renault Megane Sport? Nope. Okay. Well, this was quite an interesting sort of idea. So they have these different displays where you can see things like the power, and you can see the turbo boost and what gear you're in and things like that. And then the more modern one gives you this nice little pretty picture on the right there, which shows you the sort of envelope of G-forces that you've experienced as you've been driving along. And then if you move up in terms of sophistication, this is the center console from a Tesla. And I was actually lucky enough to go for a ride in one of these last summer. And it really is quite impressive because it's this like massive, like 17-inch color display in the middle, which shows you all these nice pretty pictures of the car, and you can see various things like how much energy it's got and stuff like that. 10 minutes? Okay, right, we'll move on fairly quickly then. And then if you go really up there, you can go to like the Lamborghini Revuton. And so you get much more of like a starship kind of approach. And so this is where you start looking, you go, well, actually, what does that tell me? It's got this nice idea of like, you can see on the left, it's got a tachometer where it tells you what the RPM is. And then depending on which gear you're in, you get the center bit goes up and down. And there's all sorts of other things there. So in terms of what I created, a little bit less sophisticated than the Revuton, but it gets across the information I'm trying to display. So it's nice and simple in terms of the nodes in the scene graph. Basically uses three things in the scene graph, and so there's a polygon to represent the outside of the bar, there's a rectangle to represent the value, and then I just put a red line which recorded the highest value you got to. And then if you wanted to, you could add some labels to it to give more information. In terms of user interaction, like I say, you don't want a complicated UI. So what I ended up with is just a sequence of screens which display different information. And then to move between them, you just tap the screen and it goes to the next one. That's all you do. You just tap the screen, go to the next one, and just rolls through a sequence of screens. That way, it just makes life nice and easy. Quite simple to do that. The only thing you have to remember is that if you've got things that are being displayed on the screen, you need to make them transparent from the point of view of the mouse, so that you can pick up the mouse event on the sort of basic screen. So this was the splash screen that I created. So I actually photographed the satellite navigation system as it boots up, so I could put the nice little Audi logo in there. And then I photoshopped in Duke with the Raspberry and the Java logo. Basic data was just like, as I say, engine load, the temperature of the intake on the engine, the catalyst temperature, so you can see the temperature of the exhaust, current throttle position, and also you can get the fuel pressure without any difficulty. And then for more advanced information, I just repeated the throttle position, put the engine speed in terms of RPM, and then added the torque and the power so that you could see what the effect of that was. In terms of G-force, I came up with a nice little sort of easy-to-see diagram there. So you've got a set of concentric circles. Each one of those represents half a G. So the yellow dot represents where you are at a particular time. Up is forward acceleration, down is braking. Left and right are obviously left and right. And then the one on the right-hand side is the vertical acceleration. So as you go over bumps, you can actually see the car accelerating over those. And then to graph the information, I just added a couple of graphs from the JavaFX side of things, so I could see where the things like the throttle position was going and stuff like that. Let's see, yeah, so just, I'm going to skip over this quickly. This was just in terms of getting the charts to work, the graphs in terms of colors. You have to set a bunch of CSS attributes so that you can have those either white or black for a black background. I don't need to go into this in too much detail. This is really the design that I had in terms of the structure of the code. So I had a sensor as my sort of superclass as an interface, and then different sensors, whether it's the EOBD2 sensor, the acceleration sensor, and then depending on whether I was doing testing or using the real sensor, then I could actually just subclass that to determine where the data was coming from. In terms of the view, again, have a display superclass, and then each of my screens was a subclass of that, so that I could then make it simpler for doing the interaction and changing screen. And then from the graph display, subclasses of that, depending on whether they wanted to graph the throttle position or the amount of power. The controller side of things, again, this is really just showing the way that data flows. So we've got different classes that represent the information, and then how we feed the information for whichever display so that it gets the right values. But it's fairly sort of straightforward design. One of the things, like I say, I wanted to do was to use the CAN bus to get information when I used the buttons on the steering wheel. This did not prove to be as simple as I had hoped, because it seems that for some reason people like Audi and BMW are not keen on sharing this information. So they don't publish a nice list of these are the ID numbers for the different parts of your car, these are the messages you can send to different parts of your car, and do all sorts of weird and wonderful things with it. So what you have to do is you basically got to decode it by hand, which means gathering a lot of data and then looking for where you press the button and trying to figure out what particular ID it is and what particular message is being sent. Some people have done some quite interesting things with this, and they've actually managed to do some quite sophisticated things in terms of like changing the display in the center of the dials and things like that. So just before I do the demos, a couple of things I've got ideas for future sort of directions. One is I thought it'd be really fun to integrate a heart monitor, so I could track my heart rate as I'm driving. I've got another idea for a heads-up display using sort of a half-silvered mirror and projecting information onto the windscreen. And then, as I say, some more information from the CAN bus would be useful. The thing I've been working on recently is integrating a GPS system into it. So I've actually got a GPS plugged in. Obviously, it's not doing anything at the moment because we're indoors. But there's a nice little breakout board you can get from Adafruit, which will provide you with GPS, and it's just a simple serial protocol that you can connect to. There's also a nice little board you can get which talks directly to the CAN bus. So if you pull the satellite navigation system out and then dig into the wiring at the back of that, you can tie directly into the CAN bus on the system. I'm a little hesitant about doing that primarily because it's a lease car rather than my own. But anyway. Place to go for more information, well, obviously Audi.com, unless they don't tell you the interesting information. RaspberryPi.org and JavaFX.oracle.com. I've written a couple of articles on my blog about this. When I really will try and write more on this because I do need to go back and finish off doing some of that. So just to briefly show you a couple of demos. First thing I'm going to show you. So I'm probably going to run a couple of minutes over time, but that will be all right. Okay, so this is just a video of the system in action. So I'll just show you a little bit of this. You have to excuse the shaky camera work because it was a bit difficult. I did not have a highly skilled... where's that going? I did not have a highly skilled cameraman to hand, so I had to use my friend to help. And this just shows as we're sort of driving along, this is around the Oracle office. And so you just see the different values changing. Yeah, I'm going round and round about there. And then you just switch between the displays, things like that. But I think since I am a bit short on time, rather than running that video, which like I say is a little bit shaky and doesn't really show you quite so much, what we'll do is we'll switch, so I'll show you this system working. Because the thing that I did, like I said, I actually recorded the information. So if I now do, hopefully that, yep. So just take a few seconds to start up, and then what you should see is, once it actually gets going, it's basically going to use my laptop as the data source. So the laptop plays back data based on the recordings that we took on that particular run. So that's the splash screen. And then, no, actually I'll tell you what. Hang on, I have to start the server on the other side. Hang on. Right, now let's just do that again. I forgot, I need to set up the server. Right. Okay, that should work now. Yeah, otherwise we don't get any data because there's no server to connect to. Right. Okay. Still plenty of time, 45 seconds. Come on. Yeah, right, okay, so now we should see, yeah, there we go. So you can see that the values are changing, and that's just as we're sort of driving around. And then, where'd he go? Oh, hang on, what have we done? Back here, right. And then if I just, so that's now looking at the advanced data, and then we can see the G-forces, and you see the green dots represent how far I actually managed to get in a particular direction. And then we can see there's a graph, so that's throttle position. And at some point, we'll see that I will accelerate fairly quickly somewhere. We're just driving along. It's interesting when you start looking at this data, you see how little sometimes you end up using the throttle, and then how much you use it. But okay, yeah, so there we're just seeing some data there. And then that's the power graph. Oh, look, there we go. Nice spike in the power. I think I do need to do some changes to the scale on my graph. But you can see there, obviously, I hit the accelerator quite hard there. But that's basically because I am out of time now. So hopefully that's given you some ideas about some of the things you can do with the Raspberry Pi and your car. So thank you very much.